I try and resolve this by the precise proposal that I'm going to make is that if you look at the observables, the operators that an infalling observer measures as he falls into the black hole, these operators might depend in a subtle way on the state of the black hole itself. And if this is correct, then the conclusion is that firewalls don't exist, and in fact things are the way they were in some effective field theory point of view. However, there are some rather interesting questions about observables in quantum gravity, which I'll try and bring out. Okay. So let me just give you an overview of what I'm going to say. I'd like to talk about, start by reviewing very quickly black holes and thermodynamics. That may not be necessary for this audience, but there's still some fun numbers I computed which may be useful. And I'll start by reviewing the old information paradox and how that was resolved. And I'll talk about how there are these refinements of the information paradox that have been discussed recently and what leads to this thing called the firewall proposal. And then I'll talk about how that can be resolved in this way that I mentioned. And then I want to talk about some new applications of that and some other more speculative ideas about how this links up to some themes in geometric quantization. So let me start by reviewing this whole notion of what black holes and thermodynamics are. So as the standard picture of the formation of just a simple Schwarzschild black hole is that you have some star, the star is too big. Once the star is too big, it's large, its mass is larger than something called the Chandrasekhar limit. It collapses, and once it starts collapsing, there's nothing to keep it from collapsing once it crosses this dotted line, which is called the horizon, and it keeps collapsing basically till it becomes a singularity. And you can actually picture these things exist astrophysically, and our friends in the astrophysics department study them. Our friends in the string theory department have also started to study these near horizon phenomena of astrophysical of these astrophysical black holes. In fact, we heard a nice talk about this on Monday. And the thing is that when you see these pictures, this is a picture taken by the Chandra X-ray Observatory, you see these pictures of these accretion disks which have all these dramatic phenomena around the horizon. But it's important to remember, and this is a key theme in this talk, is that the horizon of a black hole locally is very sedate. It's not actually a dramatic region where lots of ultra-relativistic things are happening and you go in there and you get burned, but rather the horizon of a big black hole locally is just indistinguishable from that of flat space. And it's important to keep that in mind when you view these dramatic pictures of black holes. And one way to see that, and this was seen early on, I think in the 1950s even, is that if you compute the Riemann tensor near the horizon, you find that from that and from something called the geodesic deviation equation, that if you're sitting at the horizon and you look at the acceleration of two geodesics which are separated by some distance d, then these geodesics start accelerating with something that goes down as 1 over m squared. And therefore, if the black hole is large enough, if you have a huge black hole like the black hole in the middle of our galaxy, or you can think of an imaginary black hole that's as large as you like, then these curvature effects are very small. You can't measure them by doing local experiments on a short scale near the horizon. Okay. And so in fact, horizons aren't local properties, but rather they are global properties of the space-time. And the way this is shown often is by means of what's called the Penrose diagram. So here you have some dust. The dust has some profile. It goes and collapses into the black hole. This is the singularity. And the horizon is actually a light ray. And here's an infalling observer, this shaded thick line. And this horizon divides the region, the space-time into two regions. This is the region A outside and the region B inside. But this infalling observer doesn't actually know when he or she has crossed the black hole and doesn't observe anything unusual. And so it's important that the horizon is a global property of the space-time and not a local property. Okay. Now as horizons were studied further, people started discovering in the 1970s that there were in fact these laws of horizon dynamics which were very similar to the laws of black hole thermodynamics. And there were these similarities that people started discovering. They noticed that if you throw in some mass into a black hole of mass m, then the change in the mass is related to the change in the area by some coefficient called the surface gravity, which looks very similar to the first law of thermodynamics. And there is also an analogous second law of thermodynamics, which is that the area always increases classically, just like the entropy always increases classically. And so this analogy was noted some time back. But then people began to study quantum mechanics. And when you study quantum mechanics, you find that black holes aren't totally black. And there's a cartoon way to think of this. The cartoon way to think of this, which is often used, often emphasized by Hawking, is that if you think of the horizon of a black hole, there are vacuum fluctuations, and you get this pair production of particles, and one particle falls out and its pair falls in. And as a result, if you have an observer sitting at infinity, he observes this flux of particles coming out. And in fact, this analogy is not just heuristic. Hawking found by doing a careful computation, doing a geometric optics computation of the collapse of a black hole and trying to analyze the final state, that in fact a black hole is not black but radiates, and radiates with a temperature that's given by 1/2 pi times the surface gravity of the black hole, which is a quantity that determines, roughly how strong the gravitational field is at the horizon. And if this is true and you connect this with the laws of black hole dynamics that I mentioned earlier, then you find that you should also associate a universal entropy to black holes, and that universal entropy, called the Bekenstein-Hawking entropy, is 1/4 into the area of a black hole. Okay? And notice that it depends, this black hole entropy depends on the area rather than the volume. In fact, there's no sense in which you can even make sense of a volume of a small black hole in flat space. And this is in some sense a precursor of what is called holography, which I'll discuss a little more as we go along. Okay. Now, we often say these words, but it's useful also to think of some numbers. And then the numbers go as follows. If you compute the surface gravity, you find it goes as 1 over the mass. So in particular, the temperature, once you put back in all the factors of h bar and c and g and the Boltzmann constant and so on, in Kelvin, turn out to be 10 to the minus 8 for a sun-sized black hole, or 6 into 10 to the minus 8. And if the black hole is twice the mass of the sun, then the temperature is half of that. Okay? So a smaller black hole is hotter, and a bigger black hole is actually cooler. And it's as a result of this 6 into 10 to the minus 8 that if you look at astrophysical black holes, all of which are larger, or most of them are larger than the mass of the sun because of the Chandrasekhar limit that I mentioned, these temperatures are completely undetectable. It's very hard to observe Hawking radiation, and that's because the numbers work out in this particular way. These black holes just happen to be very cold objects compared to the ordinary temperatures that we're used to. However, in any case, you can take this black hole and you can just apply to it the Stephen-Boltzmann law. And the Stephen-Boltzmann law tells you that the black hole evaporates. It loses energy through Hawking radiation. And the Hawking radiation, just using the usual T to the 4 formula, makes it lose mass at this rate. And therefore, if you recollect that the temperature is 1 over the mass and the area is proportional to radius squared, which is also mass squared, you find that the rate of loss of mass goes like 1 over m squared. And therefore, the lifetime of the black hole, the time it takes for the black hole to evaporate completely, scales like the cube of the mass. And this is useful to keep in mind. Once again, you can work out some numbers. It finds that a solar mass black hole actually evaporates over an extremely long time. If you put in back all the numbers, you find that a solar mass black hole evaporates over 10 to the 67 years. And someone said that's 10 to the lifetime of a human being. So it's an extremely long number. Because because the lifetime of a black hole goes as the mass cube, you can make this lifetime much shorter. And if you could take one of these big planes, these jumbo jets, and if you could collapse it into a black hole, then you would find it would evaporate pretty fast in about 5 seconds. Okay, so if you had the technology to take a plane and collapse it into a black hole, then you could actually do experiments with the information paradox and try and observe how things happen. Of course, we don't have this technology, but as theorists, that doesn't stop us from speculating about this. Okay, so this is so just a couple of points to summarize this part, and that is that black holes behave like ordinary thermodynamic objects. Black holes, even though we think of them as some exotic astrophysical setups, at least black holes in the sense in which I'll be speaking about them here are just simple ordinary thermodynamic objects. However, it's true that the timescales and the temperatures involved are rather different from the ones that we're used to. But if you forget about that and just think of a principled perspective, then this exotic supermassive black hole is not very different from a piece of burning coal, which also emits radiation and shrinks a little as a result. And this is the context in which I'm going to be speaking today. Okay, so that was probably familiar to most of you, but once again, since this may be a mixed audience, I'm happy at any point if you interrupt me if there are questions about what I'm saying and if I'm going too fast and assuming too much. Okay, so the moment you put in Hawking radiation, you get what's called the information paradox, and this is the classical picture of the information paradox. And the classical picture goes as follows. The idea is that if you take the matter that comprised the black hole that had a lot of information, it told you about how the matter was put together, what it was made of, and there was a huge amount of information and that goes into the matter that makes up a black hole. But the Hawking radiation that comes out looks like it's just universal black body radiation, And therefore, it looks like the black hole serves like some kind of machine where you put in one kind of input, you have a black hole, you get out black body radiation. You put in a second kind of input, you take in a star made of one kind of star which has more hydrogen, less helium, and another kind of star which has some other composition. And in both cases, you get a black hole and it evaporates into black body radiation, irrespective of what constituted the black hole. And this would be in contradiction, if it was really correct, would be in contradiction with the fundamental principle of both classical and quantum physics, which is that time evolution is always reversible. Now, you can evolve things forward in time and back in time. And if you have two different initial states which lead to the same final state, that would be in conflict with that. And so that looks like it's a paradox. There are other ways you can phrase this paradox. One of them is as follows. Now, if you take a black hole and you throw a library into it, so you might have a big Library of Congress, you throw into it, you had a small black hole, you had a very big library, thing became a big black hole, but then there was Hawking evaporation, and you go back to the small black hole that you had, plus some radiation. So this black hole looks like it's a machine which can convert a library. It's a perfect shredder which can convert whatever you throw it into black body radiation. And if you really have perfect shredders, that would be a problem. In all real world shredders, you believe that if you try hard enough, you can put things back together with, and you can even put Humpty Dumpty back together. But black holes look like they're perfect shredders which don't allow you to put things back together. And that leads to a paradox. The standard resolution to this paradox is the following. So there is a resolution to this paradox. And the resolution is that, in fact, really small non-perturbative corrections can fix this calculation. And this is a resolution that was articulated many times before. But in particular, Maldacena in 2001 made this rather precise in a particular model by studying a slightly different version of the information paradox involving quasi-normal modes. And one other way to say this is that if you have a very large system which has a very large entropy, then in fact you can take a pure density matrix, a density matrix corresponding to a pure state, and for a very large class of observables, you can arrange so that this density matrix is completely indistinguishable from a thermal density matrix up to corrections that are suppressed exponentially in the entropy of the system. And it's not hard to think of explicitly of examples of this kind where you have a pure density matrix that just differs from the thermal density matrix by exponentially small corrections. And the fact that rho squared is rho is a sign of the fact that this density matrix is pure. Okay? So it's not, the point that's being made here is that you can have pure states and thermal states, and for a very large class of coarse-grained observables, you can't distinguish between them. So what happened? Okay, something moved on. This seems to be a, okay. Okay, fine. So in other words, information can be encoded in tiny correlations between the Hawking quanta. So if this is correct, then you have these tiny correlations in the Hawking quanta, and they can encode information. And in fact, you expect that such corrections do exist in quantum gravity. And the reason such corrections exist, and you have very little control over them, is easy to summarize. It's the following. Let's say you imagine formulating quantum gravity through a Feynman path integral. If you do that, then you formulate it by summing over all metrics. This is some schematic kind of version of how you would do this. But it's important to understand, where does effective field theory and where does locality and so on come about in quantum gravity when you're summing over all metrics. And the answer is that effective field theory emerges because you have a saddle point of this path integral, and you work about that saddle point, and it's in all effective field theory correlation functions that you compute are essentially asymptotic series expansions about this saddle point. Okay? And however, if you're interested in non-perturbative corrections, then the notion of semi-classical space-time breaks down completely, and therefore you lose control of locality and over effective field theory correlation functions. And so you expect that there would be e to the minus n corrections, e to the minus s corrections that cannot be computed by effective field theory. And so if there is some reason, and unitarity is one such reason, to expect that there are exponentially small corrections that unitarize the calculations of effective field theory, then you would just say that such corrections exist, and in fact no effective field theory computation can control or can rule out such corrections. So this is a standard resolution to the classical information paradox. And another way of saying this is that Hawking's calculation is not precise enough to lead to a paradox, and no effective field theory calculation can be precise enough to lead to a real paradox with unitarity. Okay, now this is the old version of the information paradox. Old means more than 3 years old. So now there's a new version of the information paradox, which is the following. Okay? And the new version was developed starting with the work of Samir Mathur, actually, but then with the work of these authors at Santa Barbara and Stanford, starting really in 2012 and later. And what they were trying to say, what they've been, the argument that's being made, is that this whole notion that small corrections can fix the information paradox, where you say that there are these non-perturbatively small corrections that you can't capture in effective field theory, and those will just fix the paradox. These authors have been trying to argue that small corrections are not enough to fix the information paradox. And the best way, there are many such arguments, and I won't go through all of them, although I'm happy to describe them in detail if there are questions. But the most robust such claims are claims that are made within the context of the AdS CFT conjecture, because this is a setup where we think we understand gravity well, and this is a setup where gravity is holographic, in that you have some bulk which lives inside this cylinder, which I've drawn to the best of my drawing abilities, and there's an ordinary quantum field theory that lives on the boundary of that cylinder, and that ordinary quantum field theory captures all the details about gravity that lives in the bulk. Okay? And the best, the most robust of these arguments that small corrections can't fix the information paradox are made within the context of this AdS CFT conjecture. So I'm not going to try and review AdS CFT, but let me just try and say some things, the essential features that we will need. And these are really rather generic features. So even for those of you who don't deal with AdS CFT every day, all we'll use is this. The reason to use, to formulate these paradoxes, yes?
A question about the old version.
Yes.
To what extent does it involve any black hole physics? If I have a quantum many-body system,
yes,
that was also thermalized.
Yes.
And you have a similar issue there that a pure state basically goes to the thermal state.
Yes.
The resolution is also exactly the one.
Yes.
So
Yes.
this is nothing actually to do with black hole physics.
Yes, in a sense, except that you have a very large entropy, and so you could make the state mimic the thermal state to an extremely large accuracy. If I break up a paper into 5 pieces, I could stick them together with a sellotape, but the black hole, because it has a large entropy, can do a very good job of mimicking a thermal state. But it's true that in principle, it's a similar kind of resolution. Okay. So now in AdS CFT, the reason we use AdS CFT is because you can consider, basically because you can define standard thermodynamic and statistical ensembles. So for example, one ensemble that's useful to consider is to consider states in a finite energy range, okay, which is something that we will do often. And if you just consider states in a finite energy range, in a certain energy range that one can make precise, then you find that the Hilbert space restricted to this finite energy range is finite dimensional, and second, that its dimension grows monotonically as you change the mean energy of this energy range. So this is like defining the microcanonical ensemble in a standard statistical system. And then you expect also, and this is another feature, that in this certain energy range, if you take it to be high enough, in particular in this AdS CFT conjecture, if you take this energy to be much larger than the central charge of the CFT, and the central charge itself is large, then you find the generic states in this range. And by generic, you can make this rather precise. You can say, look at states in this range. On this, you cut off the Hilbert space in this way, take the Haar measure on this finite dimensional space, pick a state using that Haar measure. That's what you call a generic state, and this generic state corresponds to a large black hole. And in fact, it's this fact that most states at high energies that correspond to large black holes that's used to calculate black hole entropy. That's one reason why black hole entropy calculations work. What one really does is one computes the density of states in the conformal field theory, and that turns out to be the same as the black hole entropy because most states correspond to black holes. Okay? And when that doesn't happen, then these calculations don't work. So there may be systems where there are other kinds of configurations that dominate, and then these things don't work. But in AdS CFT, it's rather robust that if you take the energy to be high enough, then what's the dominant contribution comes from a large black hole. Okay, so now let me try and sketch for you the recent version of the information paradox. It goes by the following reductio ad absurdum. The claim is that the CFT has no fields, phi of x, so that in a generic state psi, this generic state psi which corresponds to a black hole, you compute correlation functions of this operator phi of x, and these correlation functions turn out to be the same as ordinary Green's functions as computed by effective field theory about the black hole background. Okay? And so this phi is actually an operator in the CFT. Okay? So the claim is there is no CFT operator that can capture for you the effective field theory correlators that you would get by quantizing a field semi-classically about the black hole background. So that's the claim that one wants to make, and this G is something precise because you can get it by doing quantum field theory on curved spacetime. And the way these arguments are made, I'll try and sketch some of these arguments, is by using just the generic properties of the quantum gravity Hilbert space that I mentioned previously. Now, it might look the way I've phrased it, the way I have phrased this particular thing, that this is separate from the information paradox. Where is the information paradox here? But really, this is still a conflict between unitarity, as I'll show you why unitarity appears here. It's a conflict between unitarity and some general properties of unitary quantum field theory and effective field theory, which leads to certain precise predictions for what you expect these Green's functions to be. So this is still a modern information paradox in the sense that there is this conflict between unitarity and effective field theory, which was what led to the old information paradox as well. Okay, so this is still a version of the information paradox.
You mean that exact equality? Do you allow corrections?
No, we allow 1 by n corrections. So the whole point of this is that you can't satisfy this to order 1. If you could satisfy this to order 1 by n, you would be happy. So the point of this is you can't satisfy this. You get order 1 differences between the left and the right. There's no operator in the CFT that even to order 1 can mimic quantum fields propagating in a curved spacetime.
And you're assuming generic separation between the points x.
Yes. I'll assume. I'll make this more precise. Yes, I'm assuming. In fact, you only need 2-point functions, so it's something very simple. Yeah. Okay. So here's a sketch of the proof. I'm just going to sketch this again. Assume that such an operator phi x existed. Okay. If such an operator phi of x existed, then you could do the following. You could say, let's take this operator, here's the horizon, and let's do a certain transform of this operator, which is roughly like a Fourier transform, but more complicated integral transform, and extract these modes that correspond to right-moving degrees of freedom behind the horizon. Okay. Now, the exact definition of these modes is not important, although you can make it completely precise. But the point is, let's say, assume that such an operator phi of x exists, then you do a particular transform to extract the right-moving mode behind the horizon, and then the claim is to argue that this right-moving mode O tilde doesn't exist. In this equation, by the way, I've written both the frequency and the angular momentum of this right-moving mode. I'm not sure why this is shaking, but I've written both the frequency and the angular momentum of this mode, but I'll usually suppress this angular momentum thing and just deal with the frequency component of this mode. So assume that such phi of x exists. If it exists, you can do an integral transform to pick out this right-moving mode behind the horizon. And then you can argue just from effective field theory that this right-moving mode has to have certain properties. In particular, if you do a large diffeomorphism and you ask how the field behaves under large diffeomorphisms, you can argue that this right-moving mode has to have the wrong kind of energy. In that usually this mode, which is an annihilation operator, would have negative energy, but these right-moving modes behind the horizon, the annihilation operators look like they have positive energy with respect to the CFT Hamiltonian out at infinity. And this looks like a rather robust statement you can make by just looking at the behavior of these effective field theory operators under large diffeomorphisms. Again, by looking at 2-point functions, and as I said, you assume that phi of x1, phi of x2 looks like the ordinary Green's function. By looking at that, you can argue that you have to have this behavior between the 2-point function of this O tilde and its conjugate has to have a certain behavior, which looks like e to the beta omega into the 2-point function with the order reversed. And however, there's something else you can say, which is that you believe that the black hole state is approximately thermal, and you picked out this state by looking at some microcanonical ensemble. Now you believe that there's some 1 by n equivalence between microcanonical and canonical ensembles, and therefore the expectation value in this trace, in this generic state, is approximately up to 1 by n corrections the expectation value in the thermal trace. But now this thermal trace you can actually evaluate by using the fact that this O tilde has a certain commutator with the Hamiltonian and using the cyclicity of the trace, and you find that you get, once you cycle things through and commute them through the Hamiltonian, that you get some factor of e to the minus beta omega, which is different from e to the beta omega. Okay. So I'm going through this argument quickly, not because I want you to follow all the details, but just to give you a flavor of how these arguments are made. So you argue that there are some general expectations from effective field theory about the commutator with the Hamiltonian and the 2-point functions, and then you argue that there are some general rules that tell you that in any unitary quantum field theory where you have general equivalence of the microcanonical and the canonical ensemble, you can kind of come to a different conclusion. And this looks like it leads to a paradox. Okay. And so this is the statement that there's a reductio ad absurdum, and therefore these O tilde operators don't exist, and therefore these phi of x operators don't exist. So I give you one argument. In the seminar in physics I'd given you another version of these arguments, but there are several such arguments, all of which come together and which are used to argue that no quantum field theory on the boundary can accommodate these phi of x operators. Therefore, what these authors, these Mathur and AMPS and others argued is that you should drop the requirement that there's some operator phi of x in the CFT, so that in a generic state its correlators are the same as ordinary Green's functions quantized about the semi-classical black hole background. And the moment you drop this requirement, you find that it's very hard to keep the horizon smooth. The moment you throw away these O tilde modes, it's very hard to preserve a smooth horizon, and you end up with this thing that's called a firewall, which is that you have this black hole horizon. All the way up to the horizon, the geometry is as it is, and just behind the horizon you have this huge ball of fire which is lurking to hit you. And if so, this would be a dramatic violation of effective field theory, which, recall, as I said at the beginning of this talk, predicts that the horizon is just a featureless place where there's nothing special going on. Okay? So these general arguments made using these reductio ad absurdum kind of contradictions suggest that you might need a firewall, or rather AdS CFT predicts that you would have a firewall behind the black hole horizon. So that's the flavor of these arguments. Are there any questions here? This may be a good point if there are questions about this. Again, as I said, I understand that the details may be too fast to follow here, but just to give you a flavor. Are there any questions about that? Okay. Feel free to stop me later as well. The one point I want to make is that what we showed recently is that if you accept these arguments, then these paradoxes don't only appear for the single-sided black hole, but also for the eternal black hole. And this looks like it's even more serious because we believe that we understand the eternal black hole quite well. Now, we believe we actually have calculations that allow you to look behind the horizon of the eternal black hole, and which suggests that the horizon of the eternal black hole is smooth. So it's one thing which is useful to keep in mind is that if these paradoxes appear, you can extend them also to the eternal black hole. So it looks like you have a rather unusual situation where there are very robust principles, just some principles of quantum field theory and unitarity, which are coming into contradiction with some other principles of effective field theory. And as I said, these contradictions can be phrased reasonably precisely. You know, there is, it's not so difficult as I did here to try and turn these into reasonably precise kinds of contradictions. Okay, so what's the resolution to this modern version of the information paradox? So I'm going to propose a resolution. The claim is that the modern version, this paradox emerges because you ignore another limitation of bulk effective field theory. Earlier I said that the resolution to the classical information paradox was that you ignored the fact that effective field theory couldn't control exponentially small corrections. But now I'm going to say that this paradox, this modern version of the information paradox, arises because you've ignored another limitation of effective field theory, which is that you can only measure certain kinds of correlation. So imagine that you have some, so imagine that you have some observer who's falling into a black hole. This observer can measure the modes of some light fields, but he doesn't really have access to all possible operators that exist in the Hilbert space. You know, it's not physically possible for this observer to measure such operators, and if he could, then there's no sense in which you would expect that these results would conform to those that you expect from effective field theory. So you can make this rather precise. What you do is you take what are called single trace operators on the boundary or some light fields in the bulk. You look at modes of these light fields, and then you look at polynomials of these modes. So you take maybe one mode, product of modes, product of k modes, but with the important restriction, which is that every monomial in this polynomial is restricted so that its total degree is much less than the central charge of the CFT, and also that the energies, all of the energies that appear in these modes, all the letters that appear into building up these polynomials are such that their energy is much smaller than the central charge of the CFT. So this is very similar to the operator algebras, the von Neumann algebras that are studied in the quantum field theory literature, except that these cutoffs are actually very important and they're crucial. So this is a truncated operator algebra, and in fact, as I'll say later, we don't know how to make this very precise, but we do know that if you put cutoffs at well below the central charge level, then everything works, but it would be nice to make this whole notion of a truncated operator algebra more precise. Okay. Now, corresponding to this truncated algebra of observables, if you're in a given microstate of the CFT, then actually you're not allowed, you're not even aware of the fact that the CFT has this huge Hilbert space which consists of these e to the n degrees of freedom. What you're aware of is the fact that you have the state psi, and then you can excite the state by acting with these operators, which remember I said was spans of these monomials, which I denote by A's. Okay. So you can measure excitations of this state in this way, and therefore you get a little Hilbert space, which is H psi, which is a little Hilbert space that's relevant for effective field theory, which is embedded inside the big Hilbert space of the CFT. And it's important to keep in mind that this little Hilbert space is the only part that's accessible to the conformal field theory. And now there's something important. Yes. No, they don't form an algebra unless you put projections. So if you put, so you can make them form an algebra by putting projections on them, but those projections will be state dependent. They'll depend on the state psi. Otherwise, they don't form an algebra, but they form an algebra in the sense that you can multiply many of those elements to get another element, but there are some elements which you multiply which will take you outside the algebra. So it's not strictly an algebra, but there is a multiplication rule for many elements. Okay. So now it's important that because the dimension of this, so I should say again, because of what C said, I'm going to talk about an algebra, but it's not strictly an algebra because of these cutoffs. Okay? But let me just say algebra for lack of a better word. If you like, I can say set, but algebra is more in line with the physical intuition, because the dimension of this algebra is much smaller than the dimension of the full Hilbert space. Correspondingly, a dimension of this little Hilbert space is much smaller than the dimension of the big Hilbert space. You can argue that in general, most elements of this algebra don't annihilate a microstate of the black hole. So you can argue for this rather rigorously by saying that, the set of states that are annihilated by these elements are very large codimension in the big Hilbert space. However, physically, this is something very intuitive. It's the statement that an infalling observer can't just make the black hole vanish by doing some experiment. You have an infalling observer, he's measuring some operators in effective field theory. All he can measure are things that perturb the black hole, but not something that can just completely annihilate the black hole. And related to this, there's a technical, so as a result, this little Hilbert space is isomorphic to the algebra. This is something that will change later in the talk. But from this truncated algebra perspective, the state psi is what the quantum field theorists would call cyclic and separating. It's separating, which means that no element of this algebra can annihilate the state, and it's cyclic in that you can, come arbitrarily close to any element in this Hilbert space by acting with an element of this algebra. But this cyclicity comes almost by construction, but this fact that it's separating comes about as a result of some physical properties of the big Hilbert space, or physical properties of the conformal field theory and excited states in the conformal field theory.
Sorry, I'm still confused about how the algebra actually acts on the field Hilbert space. So my understanding was that you take some subspace of the full Hilbert space,
yes,
and consider the action of those operator O and the product of O's on the Hilbert space, and
yes,
then just make the projection.
Yes.
But if you do that, then the product of these operators, projected operators, is not the same as the projection of the product operator.
That's correct. That's correct. So what you're referring to are edge effects. So if you project, if you put those projections, so it's true. So the correlators of these projected, the difference of these correlators will be very small if you make this algebra large enough. If I put these cutoffs to be, this difference is proportional to the cutoff. If I make this cutoff large enough, then I can make these differences very small. So you'd like to take an algebra which is large enough that these cutoffs are not important, but small enough that you're still much smaller than the size of the full Hilbert space. So this difference. So that's the statement that locality or all of these things will. That's actually an important statement. It's a statement that locality and these products of these operators and so on will all be approximate, but you can still, there's still a regime in which you can ignore this difference of the fact that you multiply projected operators or that you project the multiplied operators, and that's proportional to the cutoff. So the statement is you can make the cutoff large enough while still keeping it smaller than the full size of the Hilbert space. And that's actually an important point. It's the reason why, why you'd get subtle violations of locality, you would expect them. Yes?
So are you considering just all the operators products to be time ordered?
Oh, are these products to be time ordered or not? So I wasn't taking them to be, I was just speaking in ordering, but you could consider commutators and take other kinds of things. I'm working in momentum space, so there's no notion of time ordering naturally, and I'm just speaking in ordering. But there could be commutators that would let you, go to some other ordering usually. Yes. Okay. Good. Now, the statement is, given a particular kind of state which is an equilibrium state, I won't go into details of that, although I'm happy to explain more. You can define this thing called the antilinear conjugate map that does the following. It acts on the little Hilbert space by taking any element of the little Hilbert space which is produced by acting with A on psi to A dagger on psi. And the reason this antilinear conjugate map exists is because of what I said in the beginning. It's because psi is separating for this algebra. If there was an element of the little algebra that annihilated the microstate, then this map would not exist. You would not be able to solve the linear equations that lead to the definition of this S. So there's a physical reason that this S exists. And this map is in fact the same as the map that appears in what is studied in the quantum field theory literature under the name of the Tomita-Takesaki theory of modular isomorphisms of von Neumann algebras. And this antilinear conjugate map is rather important there. And this is exactly the same map. And then you can define these mirror operators, and these mirror operators also act in the Little Hilbert space in the following way. You take the modes of ordinary operators, and you conjugate them with this map. You have put an S and an S and put some factors of e to the beta h of the Hamiltonian, and the claim is that you get these mirror operators. So as I've stated it, I'm just stating the result. I'm not stating why it's motivated, but the claim is that you can certainly define this map, and then you can define these operators. And if you take these operators, and if you smear them in the correct way, if you multiply them together with the right kinds of functions, which you can compute again, and then compute expectation values of these operators in a state, you do get back what you had demanded initially, which is that expectation values of these fields that you constructed by using the O's and the O tildes that I constructed in the previous slide do correspond to what you would expect from semi-classical effective field theory in a black hole background. So this is explicitly consistent with fields that are propagating around a weakly curved spacetime around the horizon. So now you could ask, how did you evade this impossibility theorem that I mentioned some time back? There was this impossibility theorem that I explained. And the way this impossibility theorem is evaded is by recognizing that if you have an observer who falls into a certain state psi, the effective field theory operators phi that he measures depend on the state psi. Okay? And if you neglect this, and if you assume that these local degrees of freedom behind the horizon, these local excitations, some field excitations, are described by the same operator everywhere in Hilbert space, then you get these paradoxes. But if you're willing to accept that the operators, the correct degrees of freedom that an infalling observer uses may depend on the state of the system, then you don't get these paradoxes. And if this is correct, then generic microstates, including in particular energy eigenstates, and generic microstates picked in the generic sense I mentioned earlier, we take the Haar measure in the microcanonical ensemble and pick a state, are smooth and have empty interiors and do not have firewalls. Okay? Let me just try and explain in a little more detail. So in particular, remember I said that the paradox arises by putting together some robust properties of the two-point function with some robust properties of the trace. So in this case, if you look at R operators, and I've put a psi on top just to mention that they are state dependent, they do satisfy the correct commutators with the Hamiltonian within correlation functions. And within correlation functions, they also have this other property, this KMS condition that I mentioned at some slides earlier. However, if I take a basis of equilibrium states, and then you try and replace the sum over this basis with some trace of some globally defined operator, and there is no such globally defined operator, and therefore you can't make these contradictions which are based on this on making this replacement and then playing around with this trace by manipulating it and bringing this O tilde here, commuting it through the Hamiltonian, and getting the contradiction that we had earlier. And the reason for this is that there's no globally defined linear operator that reproduces for you the properties of these O tildes. Okay. So the summary, and this is important, is that if you're willing to, if you use an appropriate state-dependent mapping, in particular if you use the ansatz that I mentioned some time back, then this resolves all of these elements of the modern information paradox. So I'm going to go on to some newer things now, but again, if there are questions, this is a good time where we can take questions. Okay, we can come back to this later. So apart from resolving the information paradox, you could ask, do you get something new by considering this kind of setup and by considering these kinds of this construction of operators behind the horizon? And the claim is that you do. If you consider entangled systems where the CFT is entangled with some other system, and then you try and apply this construction to construct the interior of the black hole, then you find a precise connection between entanglement and geometry, and this precise connection is what by Maldacena and Susskind was called ER equals CPR, but I'll try and say something more precise now, which you get by applying this construction. So in particular, once again, this is an exercise in some sense in representation theory of these operator algebras. So you can consider some entangled state where you take the state of the CFT and you entangle it with some other system in some way. But now you have to recognize that the set of simple operators that you may be able to measure in effective field theory is expanded in that you can measure simple operators in the original CFT, and you can also measure simple operators in this other system that you entangle things with. And therefore, you get this product algebra, which is the product of these two, and the Little Hilbert space is the product algebra acting on this entangled state. But in this case, you now might have null relations. You might have null relations because, for example, if you take a particular state called the Thermofield double state, which I'll define later, but the point is that in that situation, it may be that the action of a left operator is the same as the action of an ordinary operator. And this is indeed something that often happens with entangled states. When you have entanglement, you act with one operator in one system, that's the same as the action of some other operator in the other system. And therefore, you might have these null relations. And so this Little Hilbert space is not isomorphic to the product algebra, which is different from the situation you had for the single-sided case. Okay. However, it's still true that because the state is separating with respect to the single-sided truncating algebra, that this action of the product algebra on this state gives you a set of, so there should be no J here, sorry, gives you a direct sum of complete representations of the right algebra. And this is simply the statement that you have this product algebra, there are some null relations that involve linear combination of something on the left plus something on the right acting on the highest weight state, or this base state is 0. And when you have such null relations, the kind of representations you get are of this kind. They're direct sums, but they're complete representations of the right algebra. And the reason you broke it up into representations of the right algebra is because you're interested in the experience of the right infalling observer. You could do a similar decomposition into representations of the left algebra if you were interested in the experience of the left infalling observer. And then the statement is you just take all of these representations, you define this S operator on each of these little Hilbert spaces, and then you just add up all of those S operators. Okay? And then you can try and ask, to try and get a connection of this action and entangled systems with geometry, you can ask whether these mirror modes, which are the modes seen by the right infalling observer, whether how they're related to modes that come from the left system. Okay? So you could ask if they're related to some simple operators in the other entangled system. And as a specific diagnostic, you could ask about how the commutator of the mirror operators and the left operators acts in the entangled state and how the two-point function behaves. And using this, you can work out several examples. I'll just go through pretty fast some of these examples. So for example, you can consider this Thermofield double state, which is a rather canonical state that's considered in the literature, which consists of taking energy eigenstate in the left, energy eigenstate in the right, entangling it together in a particular way, and then you find that you get a commutator of the left and the ordinary operators, which is the same as the commutator of the left operator with itself, and same with the two-point function. And if you then try and build together a geometry that reproduces these kinds of two-point functions and commutators, then you would find the standard Thermofield double geometry, the standard eternal black hole geometry, which would tell you the right moving modes seen by the right infalling observer are the same as modes that come from the left boundary up to some 1/n corrections. You could consider other kinds of states. These are states where you have generic entanglement, where you take the Thermofield state and you scramble it with some unitary. If you do that, then you find in fact that these modes are not related to the left modes in any simple way, neither the two-point function nor the commutator. And so the picture you get is of this kind, where both the left and the right observer see smooth horizons falling through, but the operators that the right observer measures here are not related to some simple operators on this side. On the other hand, there is still a sense in which a wormhole exists because there are some very complicated operators in the left CFT that can be used to affect the experience of someone behind the horizon here, but we don't know how to write down a geometry dual to that. There's some precise CFT statements you can make, and then you can write down some approximate kind of geometry dual to this. I don't even know if there should be a geometry which exactly reproduces this. There are some more exotic kind of examples you can consider. There are systems with less entanglement, where you take microcanonical entangled states. You take energy eigenstates and band and you entangle them together, and this leads to a funny kind of wormhole where low frequencies operators measured by the right infalling observer are the same as low frequency operators measured by the left observer, but not true for high frequency operators. So this is what we call a low band pass wormhole, and you can work out other such examples. A particular such example that's relevant is what happens if you take the CFT and entangle it with a set of qubits. And this is important because one of the concerns that you might have with these state-dependent operators is that you might violate linearity. And therefore, if some infalling observer was able to do an experiment to detect a violation of linearity, that would be very bad, and it would defeat the whole purpose of doing this construction. So one way to check linearity is in fact by taking your original system and by entangling it with some other set of qubits, which are these qubits which have these states that go from 1 to m plus 1, and you can do this kind of, and then you can act with some with some unitary operator, you can ask an observer to go jump into the black hole in this entangled state and act with some unitary operator. And then you can measure whether the density matrix of the qubits before and after the excitation is the same. And this test was in fact devised by Gissin and by Polchinski in the early 90s to test a proposal that was made by Weinberg to modify quantum mechanics. And they pointed out that in Weinberg's proposal, the density matrix of the qubits before and after this excitation would be different, and that would lead to superluminal propagation and would be a problem. So if you, however, in our case, our operators are not of this kind, and in fact, you find that if you do this, if you really do this construction of the CFT entangled with some qubits, you find that the density matrix of the qubits is not affected by some excitation. And this relies on what's called the eigenstate thermalization hypothesis in the statistical mechanics literature, and the claim that you take a small superposition of equilibrium states, and that's still an equilibrium state. I'm happy to explain this more, but I just wanted to mention this uses some rather robust properties of statistical systems. And using that, you can argue that the state dependence, which is something that you might have worried would lead to some observable violation of quantum mechanics, is in fact completely transparent to the infalling observer. And this is a very important consistency check. In general, if you want to say that you're asking some questions that are more complicated questions that depend on entanglement and that are not given by simple linear operators, then it's very important that the infalling observer still observes standard quantum effective field theory, and this is a sharp test of the fact. Okay, let me just say in the last 5 minutes some words about geometric quantization and state dependence, which may be of interest to some in the mathematics community. So the way to see this link between how state dependence might arise if you just try to do geometric quantization of a set of geometries is to think of a particular set of geometries which consist of this thermofield double state that I described, but time evolved with the left Hamiltonian. This time evolved states correspond to the action of a large diffeomorphism, and this is well understood in the quantum gravity literature, on the original state. So you know how to write down the geometry that's dual to all of these states, and it's in fact the same metric, but it's glued differently to the boundary. Okay? And on all of these geometries, you also know how the action of these mirror operators is. Okay? So you have a system where you have a large set of geometries, and on each geometry you know how to describe these mirror operators in terms of some degrees of freedom that live on the left boundary. Okay? This formula is not important. The point is that you do know in each such geometry, which is given by T, how to describe these mirror operators. And now one should recollect that every solution to the classical equations of motion corresponds to a point in the phase space of the theory. Okay? And this is the standard correspondence between solutions to classical equations and points in the phase space. Now in this situation, because you understand these local degrees of freedom behind the horizon on all of these solutions, what you have is a function on this part of the phase space. So this set of geometries is some part of the phase space. On this part of the phase space, it looks like you have a function. And now when you have a function in phase space, you can often lift it to an operator in the Hilbert space, and that's often done using projectors. Okay? So in particular, in the usual, if you have some phase space and there's some coordinate z in the phase space, you write down this kind of projector onto, you lift these points in phase space to coherent states, you write down a projector onto coherent states, and you lift this function to an operator by means of a formula of this kind. So this is the standard process that you follow in geometric quantization, and you might ask if that works here. But the reason this process works is because coherent states, or points in the phase space when you lift them to the Hilbert space, have a particular inner product that dies off to arbitrarily small values. And in particular, if you look at coherent states, they have an inner product that's Gaussian, and that goes all the way down to 0. In this case of the CFT, if you look at these states, which are states in the CFT which correspond to different geometries, you can compute this inner product. It's a CFT computation, so it's an unambiguous computation. You find that this inner product for small time shifts, remember this T was the evolution I did with the left Hamiltonian, corresponds to something that depends on the specific heat of the CFT, this C. So it corresponds to something that depends on the specific heat, and this C is something that scales with the central charge. So it is indeed very small, and this T squared might make you believe that in fact these things are behaving like ordinary coherent states, except that there's a fat tail. If you look at states which are separated by a large amount in this part of phase space, then this inner product fails to die off in this Gaussian way, and in fact asymptotes to this value of e to the minus s by 2. So you can take some toy models and do this computation, and there's this fat tail. So this orange curve is a semi-classical, this orange curve is the exact computation, blue curve is a semi-classical computation, and you find that while they behave, this inner product behaves similarly to the semi-classical inner product for small t, at large t, it has this fat tail. And this fat tail is what means that this expansion fails to converge. Okay? That's why you can't write down you can't lift this function in the phase space, this function in this set of solutions, to some globally well-defined operator on the Hilbert space. And in fact, so just to summarize, if you look at this set of states, e to the I h t into the thermofield, they give you a one-parameter geometrization, and if you allow yourself to take this t to be artificially large, exponentially large, then you get a geometrization of a large number of microstates. You understand how these mirrors work on each such microstate, but when you try and quantize it, you find that you get some operators that work patchwise in this set of states. So around t equal to 0, in some patch you get some operator, around some exponentially large t you get a different operator, around negative exponentially large t you get a different operator. And it's by ignoring this effect that as you move by a very large distance in the Hilbert space that you might get new kinds of operators to describe what you call the same degrees of freedom, that you get these versions of the information paradox. And if I had to give a slogan, and the slogan is in fact, it's just a statement in the CFT, it's the statement that coherent states are always overcomplete. It's a property of coherent states that they are overcomplete. But if you look at CFT states that correspond to classical solutions of the equations of motion, then these CFT states are even more overcomplete than coherent states. And this is just a fact in the CFT. Okay? And they're more overcomplete in that they have this fat tail. Okay, so I'm almost done. I'm almost also out of time. Let me just remind you, and I'll conclude with some open questions. So remember, I said that we have this pretty good understanding of black holes and black hole thermodynamics, and then black hole thermodynamics and the fact that black holes radiate gives rise to this information paradox, which is usually resolved by saying that the calculations of Hawking radiation in a black hole in effective field theory are not precise enough to lead to an information paradox, and small corrections to Hawking's computation will resolve these. But there are these more recent versions, these modern versions of the information paradox that suggest that small corrections can't resolve this paradox that you get, and there's still a conflict between unitarity and effective field theory. But as I tried to argue here, that arises because you ignore another limitation of effective field theory, which is that effective field theory can only see a part of the full Hilbert space of the CFT, and as you go to a very different region of the Hilbert space, the operators that are appropriate for effective field theory might just be different operators. And if you assume that, then you find that there is no paradox. And this assumption also gives you some rather interesting connections between entanglement and geometry. And there are some interesting ways to see why the state dependence, which is admittedly an unusual feature, arises even from a semi-classical perspective. Let me just conclude with some open questions, which I think are quite important, and actually open mathematical questions. One of them, on which we already had some discussion, is what is the appropriate way to formulate and come up with the theory of these truncated algebras? This is very important because this goes to the heart of how locality emerges in quantum gravity. If you don't put these cutoffs on these products of operators, there is no sense in which you get locality in quantum gravity. In fact, you can see this just by looking at the vacuum of AdS and setting up these kinds of contradictions. So this truncation on algebras that you get on local operators in quantum gravity is very important to see how locality emerges. It would be good to have a more rigorous theory of that. I think it would help to bring a lot of clarity to this field. Then there's another issue, which is what is the measurement? What's the appropriate measurement theory of these state-dependent operators? Once again, this issue is somewhat separate from the construction I just proposed. The construction I proposed could be wrong, but if you believe some rather robust dualities, such as the duality between this thermofield double and the eternal black hole, the measurement theory of modes of the infalling observer is rather interesting, and it must be different from the usual measurement theory, and that's because of this state dependence. It doesn't rely on the details of what I said, but in general it seems pretty clear that these operators have to be state dependent, and therefore it's interesting to try and understand what the measurement theory is. It can't be the usual von Neumann theory of just turning on sources. And then finally, it would be interesting to understand if this issue of a fat tail that prevents you from lifting functions on the classical phase space to operators in the Hilbert space arises in other contexts in geometric quantization. And I think these are interesting questions which require some inputs and would help to bring more clarity. Okay, so I'll stop here. I'm out of time as well.
Am I understanding correctly that the Little Hilbert space describes a space that are black hole plus a few
Yes. Yes.
And the definition of the operator S was just the property S8 was a diagonal Little Hilbert space.
Yes.
So you just need the existence of this operator.
Yes. The existence of the operator was not enough to form the mirrors. In addition, we had to put this factor of e to the minus beta h by 2. So the existence of this operator is enough to define a commutant, but it has to be correctly entangled, so we needed to do a little more. But the existence of this operator was a very important ingredient. Yes?
But you're saying somehow you only care about how this operator S acts on the Little Hilbert space, you don't care how it acts elsewhere?
It's not even defined elsewhere. If you include the full algebra of operators, then there are some operators which can annihilate the state. If you allow yourself to act with modes in the boundary theory, then you can annihilate a state. This usual Riechschneider theorem just doesn't hold in quantum gravity. You can just see that it doesn't hold. If you allow yourself to act with arbitrary boundary operators, then you can just annihilate the state. And therefore, this operator S can't even be defined in the full Hilbert space in some usual way. Right, that's the point. So cutoff shouldn't show up in effective field theory. Cutoff does show up if these things are secretly state dependent. So if you try and do some trace or try and do some, try and put them inside a trace and cycle them around, or try and use some global properties, then this is important. But it is important that the cutoff doesn't show up in effective field theory. Now, if the cutoff started showing up in effective field theory, then it wouldn't be effective field theory anymore. So the way the cutoff would appear, so if you want to see where the cutoff appears, you have to start inserting more and more correlators. You have to start seeing the limits of effective field theory. In particular, if you start considering higher and higher point correlators, so you start seeing these places where the effects that C mentioned happen, where the product of two operators is not inside the Little Hilbert space anymore, then you would start seeing the effect of the cutoff. So if you started considering extremely endpoint correlators of these operators I constructed, then you would see they're not behaving like ordinary effective field theory operators at all. But in low point correlators, these operators are designed so that in low point correlators you don't see the effects of these cutoffs. But the cutoffs are important because if you start considering very high point correlators or start doing some other crazy things, then they're important, then they're there, and they prevent you from these paradoxes.
I should think of the paradox as resolved sort of endpoint by endpoint.
Well, you should think of the paradox as arising if you ignore. If you ignore these cutoffs and you imagine that there are these globally defined operators, then there is certainly a paradox.
Just to be sure, so the definition of Little Hilbert space, you pick a particular microstate of black hole.
Yes.
And you act on it with.
Yes. Yes.